All right, today we've got a fascinating matchup for you. On one hand, you've got the beautiful, elegant, and let's be honest, often super difficult world of pure mathematics. And on the other hand, a surprisingly simple, almost brute force approach that a computer can knock out in less than a second. So let's get right into it. This whole thing really boils down to one big question. Is a good enough answer sometimes actually better, more useful than a perfect one? Keep that question in your back pocket because we're going to see which of these two approaches really comes out on top. All right, first up, let's meet our champion. This is the classic approach, the world of analytical mathematics, where the one and only goal is to find that single, true, perfect answer. Okay, so we're going to be talking about a specific kind of problem called integration. And hey, don't worry, you absolutely do not need a math degree for this. Just picture this. You want to find the total area under a curve. You can think of it as just adding up the sizes of a bajillion tiny little piles that fill up that entire space. Seriously, that's the core idea. That's integration. Okay, so here's the kind of problem we're talking about. And let me tell you, finding the exact answer, well, it's not a walk in the park. You need to know all these special tricks, you gotta have a real knack for spotting patterns. Honestly, it takes a ton of work to do by hand. It's a grind, but you get that perfect, precise answer. All right, now for the challenger. This is the computer's brute force method. And this approach, it couldn't care less about being elegant or clever. Nope. This is all about raw, simple, number-crunching power. The way the computer does it is so simple, it's almost funny. Instead of doing all that fancy math, it picks thousands of random spots, measures how high the curve is right there, and then just averages everything out. It's kind of like trying to figure out how deep a lake is by just poking a stick in it a few thousand times in random places. Simple, right? And this right here, this is where things get wild. A person could be sweating over this problem for, half an hour. A computer, it can spit out a really, really good answer with just a couple lines of code in, less than a second? The speed is just mind-blowing. So the big question is, how well does this actually work? Well, just look at this. The perfect answer, the one that took all that brain power, is 0.6931. The computer's super fast, good enough guess, it got 0.6916. I mean, come on. That is incredibly close. For pretty much anything you'd need in the real world, that's a home run. Okay, but that was a relatively straightforward problem. What happens when we throw it a curveball? Can simple brute force hang in there when things get really tricky? Let's find out. So check out this new function. This one's got a mean streak. See how at one end it just takes a nosedive toward negative infinity? Yeah, that's a big problem for our random poking method. Why? Because most of its random guesses are going to land in the nice, flat, predictable part, and it might totally miss that wild, super important dive at the end. And yep, the results show exactly that. Our simple, naive, random sampling gets us negative 3.67. The actual perfect answer is negative 3.70. Okay, it's close, I'll get at that, but it's definitely off. You can see the brute force method is starting to show some cracks. And this teaches us something really, really important. The answer isn't always just more power. It's not about just throwing a million more samples at it. The real solution is to be smarter. It's about where you look, not just how many times you look. So how do we get smarter? The strategy is so simple, it's beautiful. We just split the problem in two. We tell the computer, hey, see that big, boring, flat area? Just take a few samples there, we get the idea. But that tiny little section where it goes completely nuts, focus almost all your effort right there. See? We're using the exact same number of total samples, we're just being way more strategic about where we put them. So what happens? What's the result? Bam! Negative 3.70, a perfect match. By working smarter, not harder, the computer just nailed it. It's such a great example of how a little bit of strategy can make all the difference. Okay, this is all well and good when we have the answer key, right? We can just look and see if the computer was right. But in the real world, you usually don't have that luxury. So how in the world can you actually trust the computer's guess? I mean, really, if we're using this for a problem nobody's ever solved before, how do we have any confidence that our good enough answer isn't just, wrong? Well, this is where statistics comes to the rescue. There's this awesome tool called a confidence interval. And what it does is, based on all the random samples it took, The computer can basically draw a box and say, okay, I am 90% sure that the real, true, perfect answer is somewhere inside this box. It's a way for the computer to tell us how sure or unsure it is. And get this, we can test it out. Look at this table for a bunch of other really nasty problems. In the first column, you see the box, the confidence interval the computer calculated. And in the second column, you see the actual perfect answer. And what do you see? Every single time, the real answer is right inside the computer's predicted range. That should give you a ton of confidence that this method works, even when we don't know the final answer. Okay, so it's time to call it. Who's the winner in this showdown? The elegant, precise mathematician or the fast, smart sampling computer? This table right here tells the whole story. It's all about smarts versus strength. That confidence interval range column, the smaller the number, the more certain we are about the answer. So look at this. Taking 10,000 smart samples gives us a much better, tighter result than 10,000 random ones. But here's the kicker. It's almost as good as just throwing 100,000 random samples at the problem. Let that sink in for a second. Being a little bit clever has almost the exact same effect as using 10 times the raw computing power. That's huge. It proves that when you want an efficient, accurate answer, a little bit of intelligence is way better than a whole lot of brute force. So the verdict is in. And look, don't get me wrong, those perfect analytical solutions are absolutely critical for some things, like, say, quantum physics. But for most of the stuff we need to solve in the real world, the computer's fast, smart, good enough answer is the hands-down winner. It's practical, it's fast, and as we've seen, it's incredibly accurate. And that really brings us to the big takeaway here. Because this isn't just about math problems, right? It's a whole philosophy. So I'll leave you with this question. Where else in your life or in your work could a fast, pretty good answer be a lot more valuable than a slow, perfect one?